Good morning, ladies and gentlemen. Our program says it's time for a keynote presentation on Thursday morning. Let me introduce you Professor Mikko Mönkkönen, Professor of Applied Ecology at the Jyväskylä University. His broad expertise is in biodiversity conservation in the field of economics, ecology and politics. Mikko, please, the floor is yours.
Thanks, Urvas, and good morning, everybody. It's nice to see that so many of you came here after a nice party yesterday, and you look quite okay to me. So it's my great pleasure to be here, and I'm grateful to organizers for inviting me over to give this plenary talk. This is my first IUFRO Congress that I've been to, and I must say that I have enjoyed very much. And actually, I have learned quite much, and I learned so much that yesterday evening I decided to make some major changes to my talk based on the experiences during this conference. So let's see how it goes. So today I'm going to talk about solving conflicts between conservation and economic and conservation and social objectives in boreal forest production forest landscapes. My background is in empirical sciences, so large part of this work will be a case study from central Finland, but before that I will give you some background information and insights from Boreal zone. It's perhaps not necessary to emphasize you the importance of boreal forests. We know that it's fairly extensive biome. It covers 1/4 of the forests on Earth. It provides globally very important ecosystem services. For example, 45% of the world's stock of growing timber is in the boreal, and 30% of all terrestrial carbon. On top of those, boreal forests provide also other ecosystem services and other goods and benefits for human beings like game, collectibles, water purification, all sort of regulation services, and also it is important from the recreational point of view and also from spiritual aspects. Boreal forest is an ecosystem that is dynamic in space and time. Landscapes change with time. Each forest tract, parcel of land provides multiple services, and those services change in time with forest succession. Therefore, it is necessary to consider entire landscapes over long time perspectives when we are evaluating the capacity of the landscapes to provide us the goods and benefits that we need, and also the capacity of the landscape to maintain biodiversity. Few words about boreal forest and boreal forest in particularly in Fennoscandian. Forest loss is not a big issue in Fennoscandian countries. Forest cover is still very extensive. Most of the forests are privately owned, and the landscapes are dominated by production forests, because timber production is very important for national, regional and private local economies. For example, in Finland, 80% of land area is forest and has been forest for 80% for a long time. 60% of the total forest area is privately owned, and in southern Finland, more than 90% of the forest is privately owned. Forestry sector provides about 5% of the gross national value added, so it's very important for our national economy. It's also very important for regional economy and local people owning the forest owners. We heard yesterday plenary talk that at the European level, there are conflicting objectives on European forests, but that definitely holds true at the national and regional level as well. For example, in Finland, we have a national forest policy saying that we should increase timber flow from our forests considerably. For example, 15 million cubic meters of timber more than we have traditionally harvested, which means like 30% more timber is targeted in the next few years from our forest. On top of that, there is a pressure to increase also harvesting of forest fuel from our forests quite considerably. Yet at the same time, we have international and national level agreements that Finland and other Nordic countries have signed, saying that we should halt biodiversity loss by 2020 and safeguard our ecosystem services. And those conflicting objectives definitely create a challenging arena when we start dealing with landscape level planning of forestry. How do we get those benefits and goods from our landscapes at the same time? Because of the very long and intensive forest management history, boreal forests in Fennoscandian countries tend to be very low quality from a biodiversity perspective. And because of the landscape is dominated by production forest, the level of protection is fairly low. For example, in southern Finland, approximately only 2.5% of the total area is set aside of forest. So 97.5% of the forest area is intensively managed for timber production. And that's a very challenging situation when we deal with also biodiversity and other ecosystem services. You are probably very well aware of this scheme, how values and goods and ecosystem services are created from ecosystem processes. But what is intriguing here is that biodiversity is on both sides of the equation. First of all, it creates the structure on which the ecosystems function. And then again, it is on the other side, it is a good that we tend to put value on. So biodiversity is both the base on which ecosystem services flow, and it is an ecosystem service by itself. You are also probably very well aware that biodiversity is one of the planetary boundaries, and we can probably define sustainability that it is operating within the safe planetary boundaries. And biodiversity is one of the is the single boundary which we have already transgressed, and we are putting our human well-being at risk by doing that. So biodiversity has many facets and values. First of all, it has intrinsic or existence value. It has use values. It is the base of ecosystem functions and the base of ecosystem services. And as we saw, it's also the ecosystem service, a good in itself. It creates boundaries for human well-being. It is important from the resilience point of view. It is the base for long-term adaptability for global change. And yesterday I also learned that we can consider biodiversity as a tool to achieve certain management goals. Putting together all these different facets and values, I suggest that biodiversity is a measure of success. We should start using biodiversity as a common currency to put value on our actions. Customarily, we have been using money as a value to put value on our actions. For example, we have been trying to figure out what is the monetary value of different aspects of ecosystem services and aspects of biodiversity. But perhaps we should turn the whole situation upside down and start asking questions, what is the biodiversity value of the money we get from the landscape? And this is because money, euro or dollar, doesn't mean the same thing for different people. It's very context dependent, but biodiversity is less context dependent. It has more equal value to all people on Earth. And that's why I suggest we should start using biodiversity as a common currency based on which we put value on our actions. So now I will move on to my more empirical part. So the outline of the talk will be such that we know that there are conflicts between, earlier research has shown that there are conflicts between timber production, ecosystem services, and biodiversity. And the question then is how to solve it, how to solve the conflicts. I will first evaluate the conflicts in this particular case from central Finland, and then provide a method to reconcile multiple objectives in an optimal way. And lastly, I will tackle the issue of landscape multifunctionality, which is to address the question, can we really solve the conflicts within the safe boundary levels of biodiversity? Or in other terms, can we share the landscape with very intensive timber production? Our study area is in central Finland. It's a typical southern Finnish landscape. It's privately owned. It has a long history of intensive forest management. There is very little protected areas in the landscape. And it's conifer dominated, but some deciduous trees still are mixed within the conifer dominated stands. The entire area of the landscape, our case study landscape, is 45 square kilometers, and it consists 30,000 individual forest stands. We got the stand data from the Finnish Forest Center, and then we simulated all those 30,000 stands 50 years into the future with 7 alternative management options or regimes. So each one of those 30,000 stands have 7 alternative trajectories 50 years into the future. These are the management options that we used. First of all, we had this very intensive timber maximizing management type, which means something like 60 to 80 years forest rotation in central Finnish conditions. So after final harvesting by clear cutting, the site is prepared, trees are planted, and then there are 1 to 2 thinnings, and then final harvest again after 60 to 80 years in time. And at the final harvest, something like 5 trees per hectare are retained. So that's a kind of a recommendation. On the opposite end, we have this set aside, no management, no harvesting at all. And in between those 2 extremes, we have 5 alternative management, 2 with no thinnings, otherwise similar to recommended management, but we don't do any thinnings. And then we have 2 management regimes with postponed final harvesting either by 20 or 30 years. And then 1 option which is otherwise similar to this recommended management, but there are 6 times more green trees retained at the final harvest. Those of you who are mathematically talented, you can quickly calculate how many different combinations do we have. We have 30,000 stands and 7 alternative management regimes for each of the stands. Astronomical number of alternative combinations of management. And that's a challenging task to find an optimal combination of management regimes. But we have tried. And we have tried also estimate ecosystem services and biodiversity each of the management regimes can provide. First of all, we have estimated amount of timber production across the entire 50-year period by calculating the net present value of timber revenues across 50 years in euros. Then we have estimated collectible goods, and we use average annual bilberry yield as a proxy for collectible goods. We have been using statistical models to translate forest structures into yield estimates. Likewise, we have estimated carbon storage, calculated average carbon stock across 50 years period of time. We have estimated water quality regulation by translating landscape structure into phosphorus leaching estimates in kilograms. And we have also tried to estimate what is the ecosystem service called pest regulation by using tree-toad woodpecker habitat availability as a proxy for pest regulation. And this is because there is research showing that tree-toad woodpecker is an important predator of an important forest pest, namely spruce bark beetle, and tree-toad woodpecker can really regulate the population levels of spruce bark beetles. And finally, we have been trying to estimate the amount of biodiversity by using total amount of deadwood available in the landscape as a proxy for it. And this is because, well, actually for biodiversity we have several proxies, but in this particular case we opted to use deadwood amount because something like 25 to 30% of all species in Boreal zone are associated with deadwood. And in Finland, 60% of the red-listed species are associated with deadwood. That's a reason why we think that total amount of deadwood is fairly good proxy for biodiversity. These figures just will give you an idea how much this landscape of 30,000 stand is able to produce these different goods and benefits at the maximum, when we maximize each of these objectives. For example, the total net present value of timber revenues is 204 million euros across the 50 years time period, which means something like 4,733 euros per hectare. Bilberry yield is 10.3 kilograms per year per hectare on average. Carbon stock, 103 tons of carbon on average per hectare, and so forth. Then we move on to conflicts, and we have developed an index to measure conflict, and we call this index tolerance. And it is simply a measure or number showing how much targeting a certain objective affects the capacity of the landscape for providing another objective. For example, if we maximize timber production, how much do we sacrifice biodiversity, or what is the proportion of biodiversity that we lose, or what is the proportion of ecosystem services that we lose by maximizing this one ecosystem service. Here are the conflicts estimates. Y-axis here is the tolerance index, 100 meaning that there is no conflict and a win-win situation can be found. And obviously 0 means that when you maximize, you lose everything from the other benefit or objective. This column here, for example, stands for timber revenue conflict with or tolerance of ecosystem services and biodiversity to maximizing timber revenue. This column stands for bilberry yield. What is the tolerance of these ecosystem services and biodiversity to maximizing bilberry yield? As we can see, there are very strong conflicts between timber revenues and other ecosystem services and biodiversity. Other conflicts are not that severe, but still we can find that and see that there are conflicts particularly between bilberry yield and other ecosystem services. So, for example, when we maximize pest regulation, we tend to lose quite large proportion of bilberry yield. So, how to solve these conflicts? And we also see that there's very weak conflict between water quality regulation and other aspects. So, how to solve this conflict? How to find a compromise solution? This is an example of the method that we have been developing. In this example, we have only two objectives, for example, timber and whatever is the other objective. And we have maximum landscape capacity for both of these objectives. And this star here means the win-win situation where both of the objectives can be maximized. But because there is this conflict, this win-win situation is not achievable. And all the combination of management actions across the 30,000 stands will produce a solution that is fairly well below this win-win situation. There is so-called optimal production frontier above which no solution exists. And most of the solutions are actually below this optimal production frontier, which represent a set of Pareto optimal solutions to this two-objective optimization problem. But we can try to find a solution that minimizes the distance from the win-win situation. And this we called compromise solution. And in this particular case, this is the compromise solution that provides, that minimizes the distance away from the win-win situation. And this fairly simple method can be generalized to n-dimensional problems. So it's not just two objective optimization tool, but can be generalized. So we go back to the conflicts. We saw that there were some strong conflicts, some weak conflicts, but perhaps the good news here is that most of the pairwise conflicts are solvable using this method. So light green bar here denote the benefit of finding the pairwise conflicts. If not removing the conflict altogether, we can considerably at least ease up the conflict between alternative objectives. So first set of conclusions, maximizing timber production is in strong conflict with ecosystem services and biodiversity. And there are some conflicts between other ecosystem services. And solutions can be found that will to large extent solve the conflicts. But that will require very careful landscape level planning, and the message here is that I haven't shown the results, how we should modify our management, but the general message is that we should diversify management. No single management option is able to solve the conflict. We should use a set of alternative management options. How about the multifunctionality? Can we maintain the flow of timber and ecosystem services within the same safe boundary levels of biodiversity? Or, in other words, can we share the landscape between alternative objectives? I will use this conflict between collectible goods and pest regulation as an example here. Here we saw that there was a strong conflict between pest regulation and bilberry. For example, when we maximized bilberry production, something like only 70% of the pest regulation could be achieved. But this conflict can effectively be solved with the method that I just showed. So the next question is, what if we set a biodiversity constraint? And in this case, we set a biodiversity constraint requiring that we set aside 5% of the stands with the highest deadwood volume. And this 5% rule is taken from the FSC certification rules. And on top of that, what happens if we try to maximize timber revenues within those constraints? We can see here that the conflict is still solvable. The conflict between pest regulation and collectible goods is still solvable within the biodiversity constraint, but adding the maximizing timber objective actually aggravates the conflict. This is not just a specific case for the conflict between pest regulation and collectibles, but it also applies to other more severe conflicts like the conflict between carbon storage and collectible goods. So we can draw conclusions that multifunctionality, about the multifunctionality, the landscape can provide multiple ecosystem services together with biodiversity, but not with very high levels of timber production. So landscape sharing with timber production is going to be very difficult. Next question is how much ecosystem services and biodiversity is possible to obtain at different levels of timber revenues. Let's first look at the pairwise conflict. For example, between timber and deadwood, there is a strong conflict. So when you maximize either timber or deadwood, you tend to lose quite a large proportion of the other objective. But this can be effectively solved, and with careful landscape level planning, for example, it's possible to increase deadwood availability with very little costs. Conflict between carbon stock and deadwood, there's practically no conflict, and the conflict between timber and carbon stock is very strong and difficult to solve. So whenever you increase either of the objective, you tend to lose quite much of the other objective. So that's difficult to solve. How much carbon and deadwood is possible to obtain? We can see here that when timber objectives are greedy, very small proportion of carbon and biodiversity objectives can be achieved. And even with fairly modest timber objective, like only 80% of the maximum timber revenues, we still remain very far away from this win-win situation for carbon versus biodiversity conflict. Only when we give up from timber constraints, there is little conflict between, we can achieve very close to this win-win situation. Giving up timber constraints doesn't mean that we lose all the revenues. In this particular case, we can still have something like 40% of the maximum timber revenues. But that's when the timber objectives are secondary to carbon and biodiversity. So to maintain biodiversity and flow of ecosystem services and timber from our production forests, we need to give up the all-encompassing objective of maximizing timber production everywhere. That means either landscape sparing, which is we separate or segregate spatially landscapes with emphasis on intensive timber production from landscapes with emphasis on ecosystem services and biodiversity. Or we give up on every single landscape, we give up the maximizing timber production altogether and try to figure out what is the balance between objectives that is able to provide this multifunctionality at the landscape scale. There are a long list of future challenges for our studies. I will not go through them because the time is getting short. I would like to acknowledge my collaborators, Boreal Ecosystems Research Group from the University of Jyväskylä, and our collaborators in Jyväskylä, Kaisa Miettinen, and in Poland, Dimitri Podkopajev. Dimitri is responsible of running the optimization calculations. And our research is funded by the Academy of Finland and Konensäätiö. And thanks for listening. So far we haven't. This spatial aspect is one of our future challenges. Obviously, we have been we have been doing some preliminary analysis, for example, between habitat availability and connectivity for certain species, and we have shown that there are conflicts between connectivity and habitat availability. And that's very intriguing future challenge for our research, how to incorporate spatial aspects, management for connectivity. Does it create extra conflicts?
Has Finnish forest policy addressed this planning issue?
Not yet. But the good thing is that, as you know, in Fennoscandian countries, we tend to have very good connections to our politicians and landscape planners. So I hope that in the future we are able to communicate our results to politicians and landscape planners and start kind of discussing how to put things on practice. That's actually one of the challenges, policy tools to put things in practice as well.
Thank you, Mikko.
Thanks.